I know, but we do have to get some polar done. So what we're going to start with is just a little review of vectors. So remember, for parametric and vectors, we're just talking about writing our x and y equations differently. Vectors just put our overlay of kind of position, velocity, acceleration on there. Everything kind of worked like we wanted it to. So to get a position vector, we took a derivative, to get from position to velocity, from velocity to acceleration, we took a second derivative. So that was really exciting and fun. If we wanted t equals something, we just plugged in that number. So for example, part A of this gives you velocity stuff, and it's like, hey, find the acceleration vector. Just take a derivative, plug in a number. It's as easy as that. The big learn on this first page was from that magnitude of the velocity vector, aka speed. We take both of those components, plug in our number, square them, add them, square root them, because it's Pythagorean theorem. So if you are looking at the very first question, part A, asks to find the speed of the particle at t equals 3, it'll look a lot like this top one, except I already took the derivatives for you. Just like in regular coordinates, rectangular coordinates, if you will, when we want to find distance traveled, we want to integrate speed. So that just looks a little crazier here because our formula for speed is a little bit different. So if you're finding total distance traveled, like part D of this question, maybe look at this example. We did some particle at rest, which is very exciting. That was when both of our velocities, the x coordinate and y coordinate of our velocity was equal to 0. And this last one is just like part C on here. So let's find some position. All right. When Austin or James or Nicole or the San Julianos, do you run or just throw? You. Oh. I know you run. So when they're on the track, how do they know what their position is? If they have run a certain amount of distance, they need to know where they started and how far they went. Yes?
Yes.
All right. So we're going to take where they started and add on how far they went. We have a velocity vector here that's split up into how fast we are going in the x direction and the y direction, and we have an initial position. So I'm going to do the x part, and then I'm going to make you guys. Does everyone have a calculator?
Yes.
No.
If you don't, go grab one, because you're going to need it today. All right. All right, so let's talk about the x position. What was the starting x position? Look at the question, find it. You guys agree just that it is 7. We started at 7, and that was at t equals 0. Now we're going to add on how far we went. How do I get from a velocity vector back to position stuff? Figure out how far I went. What calculus thing should I do? An integral. I'm going to integrate the x part of this velocity vector. I asked you to get a calculator because we're not going to do that by hand. What is glaringly missing from our answer? Bounds. What should they be? 0 to 1. Let's think about the letter that's in our question. Our variable is t, so we want times on those bounds. We want time 0 where we started, time 1 where we're finishing. Let us all integrate together and see if we get the same. I'm going to do it on my handheld calculator. I'm going to do both. So I'm going to get a final number. It's very simple. Thank you. It was left here years ago, so I decided it's mine now. This is my favorite business present I've ever gotten, other than my dog. It's a good second place. All right, did you guys get a very simple number? That is slightly less than 7. Did you guys get 6? Thrilling. All right, tell me what to write for the y coordinate. How should I start the y coordinate? What? Why would you do that? Don't forget now. You're supposed to be one of my 5s. All right, let's start with y. What should I start the y coordinate with? -4. All right, what should I add on? An integral. Bound's the same? Time's still the same. And what should I integrate? Oh, you even got the dt on there. All right, let's all integrate it, see if we get the same thing. Yeah, so once we plug into the calculator, and this is going to be true today with polar as well, it's a really good question. Whatever letter we want as soon as we get the integral. So you can be extra and use t, but you're more than welcome to just use x. Now, this is something I would be comfortable asking you to do by hand, but for the most part, oh, that's very simple as well. Did everyone get a simple number? Is it? All right. I heard 3 different numbers, so I'm a little concerned. You got 9? I got this. Okay. All right, so we get a position here. I'm going to write the position like they wrote their position. So I'm going to write 6, 3. Silly goose. Plus -4.
So the x1 is just the first derivative and y1 is the second derivative?
So this is like x coordinate, y coordinate.
Oh.
So instead of like, all right, so that's like part C of this. The last part that I'm going to ask you to do, let's see if we can figure out what it is so I can give you a hint before you get going. It says, find the slope of the line tangent to the path of the particle at t equals 3. How do I find the slope of the line tangent? It's right here. I'm asking you how to do it so that when I give it to you, you're going to have an idea. All right, ready? We're listening. Everyone stare at my face. Make it weird. All right. Fine. So you don't have this question near you. I'm just going to ask it, and I want you to tell me what to do. Find the slope of the line tangent to the path of the particle time t equals 3. Okay, derivative. Good. How do we do derivatives in parametric? How do I find dy dx if I have an x coordinate and a y coordinate? Dy dt over x dt. Brilliant. What does the at t equals 3 part mean? Plug in 3. Cool. All right. You ready? There are 4 questions. I'm going to be nice and give you 10 minutes. That is over 2 minutes a question. You may use your calculator to do the position. So part 3 is exactly like this. Let's roll. You can do it. Work with your neighbors if you want. You can do it. If you have your 10.29 and you're telling me you're about the last one, it should take approximately what? Okay. I thought you saw
Well, also.
So magnitude of the velocity vector also.
What?
And then we take the T. Oh, I did I was saying that we marked it out as
Do those two.
I'm gonna get, you're not asking for magnitude, right?
She starts it like this, where she takes the time to go back. If I don't get to take it.
Oh, acceleration is the same. I was thinking velocity. Oh, speed is big. So that's double. Yeah, that makes it. This just like this.
Is this already the derivative?
Yes.
So we don't need to take this.
Correct.
Until we get to the acceleration. Did everyone catch the part A asking for 2 days? Yes.
I can do.
Oh, I remember that.
Oh, okay.
No, you did.
Did you check your calculator? Is it in radians?
Oh, that's wrong, but that's just like the life.
Like a TML.
Oh, so then you buy.
Like a DT. Anything on the AP test?
Now we have to do it.
Would you like to take
This acceleration thing is how you write. Oh, it's.
So if I didn't ask for like, okay, the vectors. Alright, we're halfway done. Are you halfway done with your questions?
No, I'm almost on A.
B.
So
you're finding the magnitude of that vector? You don't have it
Yeah, but we don't. Yeah, this is.
That's all?
I mean, it is 0 plus 4, 0.14 squared. Yeah.
Derivative of 4. The derivative of sine squared is not.
I just wanted to
No, I'm saying the derivative of
But it's still like T squared on the inside.
What's the degree?
The slope of the tangent line was dy dt over dx. Is that what the original?
I just did that. Right, this. Plug them into this. I think this season.
No, I just want to remember where.
Is this one? Oh, yeah. Is that?
Did you get your 0.0317?
Oh, yeah, derivative and derivative. So two separate things.
Easy. Wait.
So you don't, for a vector, you want to write like this. That's magnitude. So vectors should be written. You actually want to.
Wait a minute.
Sorry, the derivative.
Taking a derivative.
Wait. Are we gonna wait? We just plugged it in. I should go.
No, that's. You divide them, that's short. This is not. You don't want it. Just
I will collect these in 5 minutes.
But this one, this one, this is fine. This is only. So you talk to you got part. Wow.
Oh, so there is no
Or sign.
Oh, he's already.
Or not the resident, anti-derivative. Anti-derivative.
Anti-derivative is negative.
Yes, that's what you said. Hold on. I know you said that. You said that. Saying that's what you're saying. Yeah. That's what you said.
I'm going to start my derivatives. Is that correct? Oh, I can see that. Here it is. Integrate. Really?
Oh, wait.
Why are you sure that?
I didn't
There we go.
Yeah.
So the reason we do this hire is for.
Hello.
I'm supposed to go into the half of the part. So it is, the derivative is not. You're calculating.
Plus, here's so. Where? It bothers me. I don't put meters per second. It really does. It's like, let me see so basically, whatever. Great.
Well, like, I guess, it's like this. And 42.
All right, I'm gonna do 2 rounds. I'm gonna come around with new notes, then I'm gonna come around to grab your notes check. If it's ready to go, I'll take it as I grab your notes. Or finish up what you can, and I will grab it on the second round.
Oh, yeah, it just changes depending on. Okay.
Is one of the positions gonna be like a Greek decimal? Okay.
Yes.
If you are finishing something up, I'm gonna walk around again. All right, as I walk around now, I will take your notes check. Did I forget to give you guys notes? Of course I did. How dare for you to make you guys my memory.
I think. As you go slow, I was wondering, is that because nothing does to the result of the line change? The line change is the first one. I mean, that's the slow one, the first one. I don't know. This is why I hate the Yes.
I gotta go back to.
I would rather not do out.
I'm never going back.
I'm gonna do it. What are you doing there?
Yeah, basically, yeah, you remember we used to catch some strays? Yeah, I never had him. Oh, gosh, yeah. Yeah. We'll see what's what night. Well, they can't do it, they're just saying, like, once you get they take away your no, that's a completely unrelated.
Not a thing.
So I guess now you.
Irrelevant.
Yeah, but then we can record the coordinates, but do we not like decide? Where'd you at?
All right, if you still have your notes checked, I want to take it out. All right, last call. All right, so I'm going to philosophize about polar for the rest of the time. So polar, weird. We are going to talk about a lot about the radius, or yeah, that's what I wanted today. So the R, but polar is essentially a different way to graph points. Yes. So if you took the mock exam, you might have seen a couple of questions. It gets a little weird. The graphs get a little cooler. So instead of graphing a point by graphing x comma y, you can graph a point by doing r comma theta. So you guessed it, the unit circle is coming back in a little bit of a vengeance here. But most of these questions are either calculator questions or are you grasp straight away. So we're just going to talk a little bit about kind of the stuff that you need to be able to use polar. And then we're going to jump right into some questions specifically about this R part, because that is the focus of a ton of the most recent questions. Did I not give you guys notes? All right. I skipped like all the tables today. So the first thing we're gonna do is plot some points. I would never. All right, so let's talk about how to plot a point in polar. I actually think r comma theta is kind of an annoying way to plot these points because you really need to locate your angle before you count out the radius. So what I'm going to do to plot point A, I'm going to plot it in bright red so you can see it, is I'm going to go to the angle 2 pi over 3, which is right here, and I'm going to count out on those circles. I'm going to count out 4 spaces. 1, 2, 3, 4, and I'm going to plot that point. So that would be point A. Very exciting. You may ask, why would I ever do that? Good question. You can make a lot of really cool graphs this way. We're going to investigate some of those graphs next time when we start integrating in polar, but you can get a lot cooler graphs. I will show you some on our break. All right, let's do B. So I'm going to locate 7 pi over 6. That's right here. Out 3 circles. 1, 2, 3. That's where B is. Thrilling. All right, let's kick it up a notch. C, I'm going to locate 5 pi over 4. That's here. What the heck do you think I do for a negative radius? Go to the other way. So instead of counting out on this line, I'm going to kind of count out on the line pi over 4 because that's the other direction. So I could count out 2 that way. So this is point C. So one interesting part of polar coordinates is we can actually define points in multiple ways. So I could define this point positive 2 pi over 4. It's the same exact point, but with very different coordinates. So you can kind of get wild with how to plot points. And so these graphs often cross over themselves quite a bit. All right, why don't you take us? Oh, actually, let's just talk it out. Last color, what do you think? Nice. All right. Negative pi over 6. Where's that? 7 pi over 6. So remember, we can count kind of backwards. You can always add 2 pi to an angle. And I could count out 2 there. So what's another way I could write that point instead of 2 comma negative pi over 6? All right, I could do 2 comma 11 pi over 6. Can anyone get more creative? Yeah, so you could do like negative 2 comma 5 pi over 6. So there's a lot of different ways you can do that point. So you're going down the negative part. Because what? That's the angle part. So you're going to whatever angle it would be on the unit circle. So like the negative pi over 6 is just down a pi over 6. And then you count the radius. All right, so other things you theoretically should remember from pre-cal. I'm going to draw a triangle. Do you like my triangle? The right triangle. Not really pre-cal, this is more geometry. I'm going to call this angle theta. I'm going to call this x. I'm going to call this y. I'm going to call this r for radius. Yeah, Pythagorean theorem. So let's talk Pythagorean theorem. Which Pythagorean theorem is going to help me with which one of the 3 on the left-hand side of that table? Yeah, x squared plus y squared equals r squared. Perfect. Can you write down on your paper what you think cosine theta and sine theta equal? I will wait approximately 30 seconds. SOHCAHTOA if you are confused. What is everyone wearing for Adam Sandler Day? All I know is my feet and legs are so warm right now. Why are sweatpants so warm? Is it fair? Is this a good look? Probably not. It doesn't help. My ugly cat muscles. All right. What'd you write for cosine? X over R. What'd you write for sine? All right. So we are often going to want to talk about the x coordinate and y coordinate of a point because polar is kind of confusing. So usually we're going to relate these back to each other. So I'm just going to solve for x right here by multiplying by r. So x is going to be, bless you, r cosine theta. Similarly, y r sine theta. You will want to have those memorized. We will be using them very often. All right, if I wanted to solve for r in the last one, what would I do? Square root. This one won't be as important. I don't even think it's going to really come up today. But you can use these formulas to kind of transition equations between x's and y's and r's and thetas. We're not really going to do that. What we're going to focus on for the next few minutes is interpreting r. So r is our radius. You might have noticed that represented kind of how far I went from the origin, which is also called the pole for polar, like the North Pole. The r, that radius, represents the distance any point on our curve is from that pole. So I looked at the most recently released polar questions from the AP test, so from actual free responses and from the questions that they've been asking in a lot of their questions on AP Classroom. And I kind of tailored these notes to help with those specific questions. And they've been asking a lot of questions about interpreting R. So we're going to try a few of those. Maybe we'll try 2 before we take a break. And then we're going to kind of talk about derivatives. So here we have a polar curve, kind of looks like an egg. In polar coordinates, this equation is given by r equals 3 over 2 plus sine theta. It's not important that we can graph any of these. That just gives us that function. The first thing we're going to do is find dr d theta. What do you think that means? Take a derivative. Now, we don't need to be scared because we're going dr d theta. We're taking the derivative with the letter that's already in the problem. So this is not really a polar question at all. We're just going to take a derivative. Now, personally, for me, I am going to move the denominator up because death to quotient rule. If I move it up, what exponent will it have? -1. Long live chain rule, the winner of all of the rules. Exactly. So when I take this derivative, I am going to bring down the -1. I am going to, oh, we are lagging. Excellent. Subtract 1 from my power to get -2. And I'm going to multiply by what? Cosine theta. Also, for all of you people who always ask me, can I please write this in x's and y's instead of thetas? No, you cannot. Polar. All right, I'm going to rewrite this as negative cosine theta over all of this squared. So part 1, check. We have found dr d theta. This is now asking me, as theta increases, on what intervals does the distance between the origin and the point r comma theta increasing? That doesn't even make sense when I write the question instead of, is the distance? Yes. So this is essentially just asking us to find when something is increasing. Great. I have very good connection to some AB calculus. How do I find when something's increasing? All right, what's positive? Yeah, so I essentially need to find when dr d theta is positive. How could I figure that out? What tool might I use? That would help. How can we find those intervals? Think back to like maxes and mins and maybe. Yeah, critical values would be helpful. How can I find the critical values of this? Yeah, let's just set the top equal to 0 to find my critical values. What's going to go on that sign chart? And here's the fun part. We now get to remember some unit circle stuff. Where is cosine 0? We're going from 0 to 2 pi. Someone already said the right angle. Pi over 2 is one of them. And 3 pi over 2. All right, we're going to cut ourselves off at 0 and 2 pi. Most of these graphs do kind of complete themselves from 0 to 2 pi, so oftentimes you'll see those as endpoints of this graph. All right, let's plug in some stuff. Now, when we're testing the signs, one thing I notice is that the bottom of this function is squared, so I don't really need to check the signs at the bottom. What is cosine theta between 0 and 2 pi, or 0 and 2 pi, 0 and pi 2? Is it positive or negative? Cosine from 0 to pi over 2. It's positive, so that -3 is going to make that whole thing negative. Between pi over 2 and 3 pi over 2, what is cosine? Negative, so that -3 makes us positive. All right, and then from 3 pi over 2 to 2 pi, cosine is positive, so this whole thing is negative. All right, so you tell me, what's the answer to this question? As theta increases, on what is the distance between the origin and the point increasing? All right, increasing on pi over 2. I'm going to hard bracket those because we're talking increasing, decreasing. And it says justify or give a reason. So why did we choose that? All right, let's give him a name. Who is positive? dr d theta is greater than 0. Answer. Most of the time, or you'll be given some sort of specific interval. Yeah. Mm-hmm. Yeah. We could also check by graphing in polar, but usually that's not super necessary. I think I pulled this one from like part C of a question and the interval was up farther. All right, let's do one more and then we will take a short break. All right. You know what else we can do with polar? Related rates. Why not? What a good review. This is actually really not hard at all. So we've got a part along a polar curve. It's r equals 1 minus 2 cosine theta. Do you want to know what that looks like or do you care? All right. Desmos can actually graph in polar if you're interested. Your calculator can as well, but I'll just show you Desmos. I'll show you your calculator next class. So r equals, what was it? 1 minus. Does anyone think they know what it's going to be? Theta. This is called a limacon. All French with the polar. It's called a limacon with an inner loop. That's the loop. So we are looking for dr dt at theta equals 2 pi over 3. 2 pi over 3 is kind of up over here. So we're kind of looking for dr dt, so the rate of change of that radius around there as this particle is moving. We do know that d theta dt is equal to 2. So again, though this has r's and thetas, this is not a scary question. Dr dt telling me to take a derivative, but now I'm doing it with respect to t. So let's try this. dr dt. Y'all right over there? What? My face is funny?
Damn.
Wow.
That's not what I'm such a surprise.
At what? Thanks. It's okay. I feel like I'm in high school gym class right now with everyone in the. Do you guys just get to wear whatever clothes you want to gym now? Okay, so back in the day, we used to have these like gray shorts and a gray shirt. So I feel like I'm back in like freshman year. Yeah. Like also the worst color when you're sweating. Like
your last name written in Sharpie, so I had dick in massive writing. all the 8th graders would walk by and like, what is this kid doing?
It's a solid story. It's a solid story.
After this,
All right.
you need to go back and YouTube
Yeah.
Oh, is this recorded?
Yeah, that's fine. Yeah.
Yeah.
All right. Let's take a derivative. So I'll do the hard part. The derivative of 1 is 0. What's the derivative of -2 cosine theta? All right, 2 sine theta. I like your removal of the negative because the derivative of cosine is negative sine. Now the problem, I took a derivative of something with thetas in it, but what am I taking the derivative with respect to? T. So what's going to go right after this? D theta dt. This is not scary. We've done this a million times. It's not scary at all. So now what do we do? Well, I'm guessing I want to plug stuff in. I want to know what dr dt is, so I'm going to keep that there. I have an angle, so I'm going to plug in 2 pi over 3. And I have a value for d theta dt, so that is 2. Now, one kind of annoying part here is I do kind of need to evaluate sine of 2 pi over 3. So I'm going to give you a second to think about that because it asks me to interpret this answer. So I can't just kind of leave it and be like, oh, this is just the rate of change of r. I need to know what it is so I can say, are we increasing, decreasing? What are we doing? So I know it's 4 times something. For your edification, 2 pi over 3 is right here. In about 15 seconds, I'm going to ask you what the sine of 2 pi over 3 is. I'm going to hope I get the same answer from everyone. You may converse. All right, are we ready? Cheater.
Give them a decimal, so that doesn't really help.
It does because there's only 2 choices and only one of them is a decimal. All right. So let's start with sine. Is it the x value? Y. So is this answer going to be positive or negative? Definitely positive. What are our 2 choices for numbers? Square root of 3 over 2 and 1/2. Which one is it? Perfect. All right, so this I'm going to simplify into 2 root 3. Really, the part that I care about is positive. Now, we do want to check actually one more thing because of how polar coordinates are interpreted. So my temptation right here would be to say that interpreting my answer that the radius is increasing, but remember that that radius can be negative. So a negative radius that's increasing is actually kind of approaching the pole. So we do want to check and see what the value of r is at 2 pi over 3. Let's just do that real quick to check and see. That's 1 minus 2 cosine of 2 pi over 3. All right, let's put our big brains on. If sine of 2 pi over 3 was square root of 3 over 2, what is cosine of 2 pi over 3? 1/3. All right, so that's 1 plus 1. I get 2. So what is happening to this particle? I do as well. So is this particle's radius increasing or decreasing? It's increasing. It was a positive radius, and that positive rate of change means it's getting more positive, meaning we're going farther away. So we are getting farther away from the origin. So how would I write this? You could say the radius is increasing. I'm going to say the particle is moving away. Yeah. From the origin. Oh, nice of you to join us. And since they're going to ask me to justify, I'm going to say because r is greater than 0 and dr d theta is greater than 0. Cool. Thoughts on a break? Cool. Let's do it. Not 5 minutes. Why is my timer so big? Yeah. Because I miswrote it. Thank you.
Some more noise in your chair, please.
Well, after the
You made a friend? That would be very crazy.
Yeah.
I'm a little bit confused. Could you explain this part to me again?
The sign chart? Yeah. So what we did was we looked at this guy right here. I want to know when he's increasing. So I was going to make a sign chart to test the positive or negative of this derivative. To find these two values, we found critical values by setting that top part equal to 0. Using our unit circle knowledge, those were our two critical values. And then we plugged into this guy. I mostly just plugged into the numerator because the denominator is always positive. So if I pick a value in here or think about my unit circle, everything in 0 to pi over 2 is like that first quadrant. So cosine is positive. Positive times the negative 3 gives me that negative sign. In between here, cosine's negative since your x values are negative. So we're just testing. Yeah.
Here to here.
Exactly.
Got it.
Hello.
I'm gonna ask you, so,
Yeah.
so like on the unit circle, we get, I understand that it's over here, so we
Yeah.
know it's positive because of the like all.
Because your y coordinates.
'cause it's
Yeah.
a Y
You could do that too.
Okay.
I always just think x's and y's. So since my y coordinate is positive up here because I'm above the
Oh,
x-axis, my sign is going to have to be positive.
Because sine is a Y.
And so
value.
like that's negative because your x coordinate is negative because you moved left.
Okay, that makes sense. And our only options were
1/2 and square root
root
of
of
3 over 2. And that's for pi over 6s and pi over 3s.
right, because then this one would be pi over or 2.
Root 2 over 2.
Yeah, root 2 over 2, and then those are both of them. And the bottom one is root 2 over 2, and what's the other one?
For the axes, you just have zeros and ones. These, both the pi over 6s and the pi over 3s are root 3 over 2 and 1/2.
But they're just
This is, yeah, they're just.
Thank you.
Mhm. I don't know where that came from. It was probably found on the floor, to be quite honest. I've been told that some networks are just calling it 5G, but they're lying, and it's not actually 5G.
Because I don't know that. As soon as you say that, just as the school
So I would like the internet to stay on.
Yeah, no, it's not like that.
All right, we're back in it to win it. I'm going to skip the next question because it's a little long. We might revisit it next class. And I want to go down to the bottom because I'm going to bet no one remembers how to do this, even though I have taught it to some of you at least twice. Looking at you, and you, and you. What? And you. All right, so let's talk about this question. We got to figure out what it's asking us to do. This is another question that has a polar overlay to something you learned in AB. So I have given the polar curve, that thing. That thing, you can tell this is a calculator question. I believe this was on the 2018 exam. So given that polar thing, we have an interval. We want to find the average distance from the origin to a point on the curve. What is a different way to say the distance from the origin to a point on the curve? What is that? The radius, which is r, right? So that is our function. R of theta is our distance between a point on the curve and the origin. Again, we're spending a lot of time with this R stuff, doing some AB review, because these are the questions that are getting asked on the free responses on the AP test. How do I find the average value of that function? Average value should mean something to you. All right, it's kind of like add everything together and then divide by how many are there, but we don't add everything up in calculus. What? Yeah. No, for integrals, yeah. I just gave it away. How do we add a bunch of things up? An integral. All right, so let's take an integral of this function. What do you think the bounds are? Hold on. What? Hold on. I promise. All right, this is like the add them all up part of average value. It's like a Riemann sum. You're adding a bunch of stuff up. That's an integral. All right. Yes. Now, how do we divide by how many are there? Does anyone remember? We put something out front or underneath. Anyone remember? Well, how many are there? Well, that's a little bit of a weird thing to think about. How about we take and we divide it by the length of our interval? You guys remember 1 over b minus a, integral from a to b? You should. I've taught it to you multiple times. All right, so I'm going to do 1 over the square root of pi minus 0. So essentially we're taking the area, like Lily was mentioning, that's the area of our thing, and we're dividing it by the length of our interval. So we're getting the average height of that function, the average value of that function. Now comes the fun part. Let's see if we can all plug this into our calculator and get the same thing. Again, this is a question from a recent AP test, so they did expect you to plug this in and get it correct. I would not type with theta, because why? You don't need to. Once we get it in this form, feel free to use x's. We're just doing an integral. Everyone should try to type it. I'm going to start calling people. It should be relatively weird. Should be also relatively small. All right, you guys agree? Yeah? You can round out, that's fine. Round out, round up. So you could also say 1.580. I hate rounding when it's like that, so you will never see me round up like that. Yeah. Truncate if it's going to end in 0. Actually, I'm just team truncate usually. All right, now you're probably sitting here being like, yo, Hattie, all this R stuff is cool, but you know what would be cooler? Taking a derivative in polar. I know, it's really fancy. So we're going to try to do 2 questions between now and the end of the block. If we can get questions done, I will stop talking. So let's figure out how to find the slope of the tangent line. So not the r d theta, where I can just take the derivative because that's the variables I have. I want to know dy dx. Now, does this look familiar to how we found the derivative anywhere else? Does it look familiar from like your notes check like 30 minutes ago when you did dy dt over dx dt? It should. The problem, y is not just a thing that I know in polar. So try not to flip back to the front page, but remember what we said y was equal to with r's and thetas in it? All right, flip back to the front page and look at this little cute chart we made here and tell me what y is equal to. R sine theta. Now, the sine theta will always be the same. The r will change depending on the graph given in our problem. All right, what does x equal? r cosine theta. Now, if you're looking at that and going, wow, that's going to suck. Yeah, it just does. The derivative formula that I'm going to write down, I would really recommend not memorizing in any way because it's not going to be helpful. I just want to do it one time within just the r's and the sine theta so we can kind of see how it works, and then we're going to actually do a question. Now, the reason that this sucks is that is the derivative of r times sine theta. Why am I emphasizing the times? Product rule. So both the top and the bottom of this have product rule. There is make it nicer. It just is how it is. So these slope questions for polar is actually a pretty rough question. So we'd be doing first derivative of the second plus second derivative of the first. That r will be something we're given in the question. So that's where we would just do like the derivative of that with respect to theta. Same thing for the bottom. We'll do first derivative of the second plus second derivative of the first. Again, I would never want you to memorize this like a formula unless you're just like super great at memorizing and super terrible at product rule. Because usually we're going to plug in our r and actually do this math with product rule as we go. Because the negative sign. So derivative of cosine is negative sine theta. So I just put my negative out front. So derivative of this guy is negative sign. So instead of making it look like subtraction. All right, so let's find a derivative. So that's saying take the this thing in parentheses. All right, so let's do an actual question. I'm going to show you how I would format this because it's a lot of work. Also, this is the graph we're going to be finding the slope of at theta equals pi. So right there, anyone want to guess what they think the slope is? Guesses? -1, -2, -1.5.
It's one of those.
All right. All right, so let's find it. So I actually like to do, since this is, it's a huge derivative, I kind of like to do the dy d theta and dx d theta completely separately, kind of like we did in parametric, and then put them together at the very end, especially because I'm going to have to be plugging in trig as well. So let's set up what we think y is, find dy d theta, and then we're going to plug in theta equals pi. Some of these three things in this order. All right, remind me, what is y in polar again? R sine theta. Next class, you should all be able to say that fast, or in like 3 minutes. All right, so I'm going to plug in what r is. In this question, r is 3 plus 2 sine theta. And then I have sine theta here. All right, you could distribute the sine in this case, since it's both sine. Want to do that? Or just do product rule? Well, let's just do product rule. No worries. All right, so product rule. How does that go? First. All right, so first derivative of the second is cosine plus second the first. That is 2 cosine. Nope. As long as you have one derivative and one original function, you should be good to go. All right, let's talk about sine and cosine pi. So 3 is himself. What is sine of pi? 0. What's cosine of pi? No. -1. We're at this point right here. All right. Let's try again. What's sine of 0? Cosine of 0? -1.
That's 2.
All right. So overall,
Oh yeah, that's right, because it's times 2. Oh, okay. I'm so sorry.
Is everyone good?
So,
Sine of 0 is 0. Yeah, that's true, but not relevant. Sine of pi is 0. Cosine of pi is -1. All right, overall, this should be -3, yes? Cool. All right, let's keep going. I am halfway done. I modeled how much space you should use. All right, what is x in polar? All right, if you're feeling brave on this, race me. You're probably going to beat me since it's a lot of writing, really. All right, so same R as before. So this actually should feel relatively repetitive because the only part that's going to really change are in part of my product rule. So we're going to do first. That's exactly the same as before. Derivative of the second is now negative sine theta plus second cosine theta. Derivative of the first is still 2 cosine theta. All right, so notice that really the only part that changes between these two is this stuff right here. So you kind of get to use your work. All right, what did we say sine of pi was? 0. What did we say cosine of pi was? Negative. So this whole thing is 2. All right, now, have we answered the question? No. All right, so dy dx, we're going to take dy d theta, which was -3, and divide by dx d theta, which was 2. So, Mia, you're the winner of slope guess today. What? All right. We're going to try to do one more question, then I'm going to be done. Oh, P.S. This is called a dimpled limacon. Limacon, it's French. The C has like, I think, one of the squiggles on it. This is the dimple part. Yeah. All right. This, anyone think they know what this one's called? A cardioid. Like a heart. A cardioid. All right, so if it's pointy like that. This pointy part, we're going to talk about it in a second. Cusp. So that point like that. Did someone just say the crack? It does kind of look like a boat. All right. So we are going to do one last application. That cusp will come into play in a second. So we are going to find all values of theta between 0 and 2 pi, where this graph, which is 1 plus cosine theta, has a vertical tangent line. So you can kind of guess where those places are. It looks like right here, right here, right here to me. So I'm looking for those places, but we're finding values of theta. So we're finding angles here, which is going to be a little bit more interesting. We do get an odd piece of information, which we will talk about. They're telling us that dy d theta equals 0 at theta equals pi. We're going to talk about what that means in a second. How do I find where something has a vertical tangent line? Slope is undefined. How do we say slope in calculus? Which derivative? dr d theta, dy dx. All right, dy dx needs to be undefined. Let's go back up and look at what dy dx looks like for polar. So this is what dy dx looks like for polar. if I want to make this fraction, focus right here, if I want to make that fraction undefined, I want to make the bottom 0. I need to find where dx d theta equals 0. So this is translating find dx d theta, set it equal to 0. All right. Let's see if you guys are getting faster. What's x in polar? Cool. All right, let's make that for this one. So I'm going to replace r with 1 plus cosine theta times cosine theta. Do you guys want to do product rule or just do some chain rule? Okay. I'm just really team chain rule. Death to all other rules. Look, we made a whole big circle with our conversation. All right, so let's find the x d theta. So the rate of change of x with respect to theta. So we're going to do first. What's the derivative of cosine? Plus second derivative of the first. Derivative of 1 is 0. Sign still negative sign. And I want to set this lovely derivative equal to 0. Anyone see something that might be helpful in my solving adventure here? They both have them. Let's factor them out. Thank you, Austin, for reading. All right, what I have left is 1 plus cosine plus cosine. So I'm going to call that 1 plus 2 cosine theta. All right, I got two things to set equal to 0. Here's our unit circle again. All right, are you ready? Where is sine 0? 0, pi, and I'm going to add in 2 pi as well. All right, solving this one, I'm going to subtract 1 and divide by 2. So I'm looking for where negative 1/2. That's a little bit harder. I'm going to give you a couple of minutes to think about it. Where is cosine negative 1/2? Might be helpful to think. All students take calculus, so you are looking in these two quadrants. You're also probably looking for either pi over 6s or pi over 3s. I have a claim for it's pi over 3s. Does anyone agree? I don't hate that. All right, then what are the pi over 3s in there? All right, we have 5 answers. I'm going to argue that, well, I'm going to argue that 2 of them are the same answer. Does anyone know which 2 are actually the same answer? 0 and 2 pi, but if they're going to include both of those in the interval, which I believe that I stole a lot of these out of like part C's and D's, usually they include both of those, so we're going to include both of them. I'm going to argue one isn't an answer. Does anyone think they know which one is not an answer? Look back up at the question. I told you I gave you a weird piece of information. Yeah. Theta equals pi. Let's talk about that. So how did we find these numbers? We set the x d theta equal to 0, right? So when we were creating this fraction, we had 0 on the bottom. Well, I told you at theta equals pi, we also had 0 on the top. So is that a vertical tangent line? Horizontal tangent line? Is it anything? Is it nothing? The answer is it's a cusp. So it's going to be not a part of our answer choices. So usually this is kind of avoided on AP test questions, but you would want to make sure that you're not including any sort of cusp there. And I can see it from the picture because at that cusp, that's theta equals pi. So we're over at 180 degrees. Does that look like there's a vertical? Does it look like there's a tangent line there at all? Like, how would I draw this? Would I draw it like that, like that, like that? Like, who knows? So that's kind of what that 0 over 0 behavior is. So we would want to not include that guy. All right. So we got a little bit of an intro into polar. I'm going to tell you next class's polar is a bit overwhelming, but we're going to do it. And I'm going to try to make it as kind of simple and AP focused as possible. Let me see if I can find a picture to show you. Ah, perfect. So I can show you a bunch of different ones. Let me actually just do a cardioid. The reason next class is going to be confusing is the way that area it works in polar. So I'm going to just press play and I just want you to look at it for a second. So think area and rectangular coordinates. We go on the x's, we kind of slide and we accumulate area just from left to right, or from up to down. That's not how this works because we're going to be integrating with respect to theta, which is the angle. So the thing that's moving is the angle. So this is how we're going to kind of count out our area. We're going to be sweeping out an angle, which is a little bit weird to think about. When I say sweeping out an angle, maybe take a look at your unit circle before next time. Idea. Next class, we'll probably start with the notes check again. We may even finish with one, but we will definitely notes check at some point tomorrow. I'll have updated dates for you. Perfect. Thank you for your hard work today. I will see you guys on Thursday for anything but a backpack day. Get creative.
I want to try to bring a wheelbarrow.
A wheelbarrow? That's just obnoxious.
I know, that's what I was talking about.
I am.